So take a look at the portion under the radical here. And if you remember, we called this in our calculator program D. Okay, remember we stored it? We had b squared minus 4ac, and then we stored that into the variable d in the calculator. Okay, that made it easier for us to type the program, but we're going to define this quantity b squared minus 4ac as the discriminant. The discriminant, not the discriminate, discriminant. They're different words. Okay, make sure you spell it correctly. It comes from the Latin word discernere, which means to discern or distinguish, which merely means to tell the difference between things. So this is going to help us tell about the roots of the quadratic. Okay, so what you need to have down is d equals b squared minus 4ac. Okay, the rest of it you can read or you can talk. Alright, so d equals b squared minus 4ac. Now what I want to do for the first problem is find the roots using a calculator program and then just write down the discriminant on the side. And the same thing for the second. And then maybe at the end we can make a correlation or find a relationship that relates the discriminant to the types of roots that we have. And some of you might be thinking about that already, or might have thought about that yesterday, because we mentioned it in the quadratic program. Okay? So let's sample here. Please run this through your program. Tell me what you get. I'm going to do it on the board with the quadratic formula. And I'm going to note the discriminant at the bottom. Remember, the discriminant is b squared minus 4ac. It's whatever's under this radical up here, really. Okay? It's whatever's under the radical. So it's going to be 9 plus 4 times 4 is 16. Times 2 is 32. So it's going to be 41 for the discriminant. What do you get for the roots? What do you get for the roots here? Katarina?
Negative 2.35 and 0.85.
All right. So, how can we classify those numbers? And that's rounding, right?
Yes.
Yeah, and note, by the way, that these are both irrational because we're rounding. And because, take a look at the original quadratic formula. This would be radical 41 under here, right? Radical 41. Because the discriminant was 41, that's what this turns out to be. So this would be an irrational number, radical 41. You cannot simplify it. So these are rounded, but they are irrational. There are a lot of decimals that go on with no pattern. These are irrational. But how else would you classify them? Are they real or imaginary? Are they real or imaginary? Yeah. They're real. Are they the same or are they different from each other? I know this is very obvious, but I'm honestly asking. They're different. Okay, and you're going to see why I'm asking these. Okay? And finally, the numbers, they're irrational, but I'm going to leave that for now. So let's just say they're real and they're different. Okay, the roots. And let's just make a note of the discriminant. And maybe you'll see it as we go through the correlations, but don't worry right now. All we're doing is writing down our roots and just taking note of the discriminant. Is that clear so far what we've done? Again, roots and discriminant. Next one. Same thing, please do it. And feel free to factor out a 2. Okay, feel free to factor out a 2. To make it easier on you. But if using the program, does it really matter? No. Good answer. Again, I'm using the simplified version once I factored out a 2 out of the whole quadratic. Mike, what do you get for the discriminant? What's 6 squared minus 4 times 1 times 9 give you? Yeah, 0. The discriminant in this problem is simply 0. Anybody running through their program yet? Manny, what do you got for the roots? Yeah, negative 3 or negative 3. Remember when I asked you, are they different or are they the same in the last problem? This is why. So how can you classify these roots? They're the same, so they're repeated, right? Remember we said repeated? Okay. Are they real or are they imaginary?
Real.
Real. Imaginary would have to have the letter I next to it. So they're repeated and they're real. And what else are they in this case? Rational numbers. They're definitely rational numbers. You see that? Because you're going to have, really, this drops off. Everybody notice that? It's 0, it drops off. So your result is just this right here. The plus or minus doesn't even matter. Because what's plus 0 to any number? It's the same number. The same number, that's times 0. Negative 6 plus 0 is negative 6. Negative 6 minus 0 is negative 6. So the numerator is always going to be negative 6. The denominator is always going to be 2. Negative 6 divided by 2 is just negative 3, which is why the answers are both the same. Okay, so real, repeated, and rational. Okay, it's rational because there's no square root involved anymore. Because the square root of 0 is just 0. So it doesn't affect the problem. So let's make a note of that, and let's go on to the next one now. Okay? Everybody all right so far? So we're just listing our roots and listing our discriminant. Determine the zeros of the function. What does it mean when you want to find the zeros of the function? What do you set the function equal to? 0. Hence the word zeros, right? So at this point, we're just finding the roots or the solutions to this equation. Now, before we go to the roots, tell me what the discriminant is in this problem. What do you get if you do the discriminant? 6 squared minus 4 times negative 3 times negative 5. Triple negative remains still negative. Okay? So if you want to, take a look up real quick to make it easier on yourself. Go like this. See the double negative from the negative 3 and the negative 5 right here? Make those both positives. Because the negative times the negative is a positive. So make these two positives, but leave this negative behind. Okay, it might make it easier on you. Okay? Everybody see what I'm doing? A negative times a negative is a positive. So the negative 3 times the negative 5 is the same as positive 3 times positive 5. These two negatives become a positive, but we still have the negative there. So 36 minus 4 times 3 is 12. 12 times 5 is 60. Which is really just what? Yeah. Now, if you have a negative for the discriminant, doesn't that mean there's a negative under the radical? Everybody, what kind of an answer are we going to have automatically? Imaginary. When there's a negative under the radical, it's imaginary. Okay? So you're going to have imaginary roots here for sure. For sure. Running it through the program, what do you get? What do you get for this one? Anyone new? Katarina, go ahead.
1 minus 0.82i and 1 plus 0.82i.
Is it what? Many?
It's 8.816.
Yeah. 816 and goes on. She's just rounding. Yep. So 1 minus 0.82i and 1 plus 0.82i. So if we were to categorize these, we would say they're imaginary, right? They're imaginary roots. Aren't they also conjugates? Remember the term conjugates? What does conjugates mean? Yeah. Conjugates are like the plus or minus part. That's what a conjugate is. So these are imaginary conjugates. Okay? So, in this last problem, we had a negative discriminant, and we came up with imaginary and conjugates as roots. Can anybody get an idea of what I'm getting at? We have had 3 problems so far. We had 3 different types of roots. Can you categorize these 3 and maybe give me some sort of an if statement? If this, then this. Give me one.
If statement, general statement.
How about this? I start you with if the discriminant is.
If the discriminant is 0.
Good. The roots are.
The roots are the same.
Good. The roots are repeated, rational, and real, right? You don't have to write this. We're going to make a table. Just listen. If the discriminant is 0, the roots are real, they're repeated, and they're rational. Good. Go ahead.
If the discriminant is
and they are conjugates. Very good. And what was the first scenario? If the discriminant was what? Positive. Erickson, the first scenario, when the discriminant was positive, example 1, what were the types of roots we had? That's all right, sorry. See, Murphy's Law again, right? The one thing you didn't do, you're going to get called on. It always works that way. Help him out.
Different and, I don't know. Something with R, right? No, because like
Real.
I started writing it.
That's all right.
And then I can remember what you said.
Real. Different.
I don't know.
And sometimes irrational. We'll talk about when that happens, when it doesn't, because it can be rational there. Okay, let's make a table to show. Okay, so take a look at this table, please. What's that? Murphy's Law means whenever things go wrong, whenever you don't want them to go wrong. Like, for example, I'm running late, and suddenly today the metro is delayed or the subway is delayed. But on days when you're 20 minutes early, the subway is running great, and you make it to school in 20 minutes. Murphy's Law. Or the day you forget your umbrella, it rains. Murphy's Law. That's what Murphy's Law is. Okay, whenever something happens, it happens to hurt you. Not hurt you, but it happens like, really, out of all the days today, like that kind of thing. Okay? All right. So we have three cases. I was going to say 3 scenarios or scenarios and cases. 3 scenarios. Positive discriminant, we have 2 real distinct roots. Okay, 2 real distinct roots. What does distinct mean again? Different. Yes, different. Distinct means different. Write that down if you didn't know that. Distinct means different. If the discriminant is 0, we have 1 root. It's real, it's repeated, and it's rational. We can also call that a double root, by the way. A repeated root that occurs twice is considered a double root. You can also have triple roots and quadruple roots, etc., etc. We can say that's a double root. And if the discriminant is negative, we have 2 roots. They're imaginary and they're conjugates. Okay, so we're just summarizing. Take a look at the asterisk at the bottom, please. Note that if the discriminant is positive, so first case up here, we're looking at the first scenario now. If it's positive and it's also a perfect square, then the roots are going to be rational. And the reason for that is because, take a look, remember, if this b squared minus 4ac is a perfect square, and you take the square root of it, you're going to get an integer value here, right? And an integer, plus or minus an integer, all over another integer, is still going to give you a rational expression. So again, imagine b squared minus 4ac was 64. This radical would become square root of 64, which is just 8. And then say b was like 4, you'd have negative 4 plus or minus 8 all over, say, 10. Either way, it's going to be odd numbers or integers over integers, which give you a rational expression. So this scenario can be rational if it's a perfect square. If it's not a perfect square, then it is opposite of rational, irrational. Okay, so there's really 4 cases, but the first case is broken into 2. Again, if b squared minus 4ac were a number like 41, like the example number 1, you can't take the square root of 41 exactly. It's an irrational expression, so it becomes irrational. But if it were, say, 49, then it does take the square root of it and gets 7.
In the homework, there were a few problems.
Where b was a square root?
Yeah. Does that still apply?
If b is a square root, you're going to end up with a square root over a square root, and that's an extra case that you have to consider addition to this. So that would be one that doesn't apply. So imagine that b was the square root of 3, right? This would become the square root of 3 squared, which is just 9. And then maybe this would be like, say this is 0, whatever it is, right? Or say it's some quantity, say c is 0 or something. Yeah, sure, you're going to get that, but you're still going to have the square root there. So it still is irrational. So that's a different case. That's an exception to the case, which are the rules. If b is irrational, your roots are still going to be irrational. That's a good thing to write down. Very good. If b is irrational, so if b is under the square root, like the square root of 2, then you're still going to have irrational roots, even if b squared minus 4ac is a perfect square. So the first case, we really don't always break up because of that. So if b is irrational, Okay, for example, root 2. Okay, then you're going to have an irrational root or irrational roots. Okay, and that must happen simply because the square root, the quadratic formula would leave an irrational term here. Even if this was a perfect square and it came out to be like 8, you'd have root 2 plus or minus 8 all over, say, 10. The root 2 is what's going to make this whole thing irrational. Good point there, Katarina. Very good. And I wasn't even going to bring it up, but I'm glad you noticed it. Okay? Let's quickly take an example here. Okay, let's quickly take a look at this last example. What I'm going to do, we're going to run out of time for sure. So I'm going to pause the recording after this. And I'm going to finish recording during 4th period. And I'm going to go through the rest of the problems. We can start example 4. But I'd really like you guys tonight, please, to just listen to example 4. There is example 5 after this. Not as necessary to do. All it is finding the roots in the calculator and verifying that the type of roots are correct by looking at the discriminant, which is what you're going to do in the homework anyway. Okay? But the notes are online for 4 and 5, and I'm going to record anyhow. But let's take a look. We have this equation, kx squared plus 8x plus 4k equals 0. And it has different roots when the value of k is different, which makes sense. If you change the coefficients for a and c, it's going to give you different roots. Find the values of k so that the equation has the following. First, a double root. When did we have a double root? What's another word for a double root? Repeated. Very good, Summer. Repeated root was when the discriminant equaled what? What was it? 0. So for case A, we're looking to know when the discriminant equals 0. So let's find the discriminant at the top and list it. The discriminant is b squared minus 4 times a times c. Please take a look at the top, make sure that makes sense. A is k, c is 4k. So here's the discriminant. Everybody agree with me so far? In variables, the discriminant is 64 minus 16k squared. Now, if we set that equal to 0, because that's what case A tells us to do, right? It says the discriminant equals 0. Well, this is what the discriminant equals. So by the transitive property of equality, or the chain rule, these two things must be equal. So set this equal to 0. Divide by 16. Square root both sides. So what are the values of k? The values of k are 2 and negative 2 that cause double roots. And at the end, I'm going to record the rest of this, but I want you to check it by running these numbers through the calculator. So plug in the positive 2 or negative 2 into the original and run them through the program. I'm going to do parts B and C, and then I'll do example 5 as well. So watch it tonight. It'll be about 10 minutes of watching. The homework's already on Moodle for this section, so make sure you practice tonight. Are we all okay with this? Okay? If you need help today during a free or during a period, I have gym duty today during 6th period. If you have lunch and you need help on something, come by, please. Okay, and office hours tomorrow, don't forget, please. Alright, so let's continue with part B now. We're looking for an answer that has 2 different real roots. So, again, with part A, we already defined the discriminant as 64 minus 16k squared. And if we want a solution that has 2 different real roots, we need to remember that that is indicated by a discriminant that is positive, or simply greater than 0. So we're going to set up the problem the same way as part A, where we look for a double root, but there we set the discriminant equal to 0. Now what we're going to do instead, though, is set it to greater than 0. So for part B, let's say 64 minus 16k squared is greater than 0. And what you're going to notice is when you solve this, you're going to get the same general solutions, but as we called those, remember, we called those the critical points. So we're saying 64 is greater than 16k squared. Divided by 16 gives us the 4. So the critical points are still plus or minus positive 2. Plus or minus 2. So these are our critical points for k. Now, we have to remember that when we have a quadratic inequality, we have to test those critical points, or test regions about those critical points on a number line. So let's immediately draw a number line. Let's identify our critical points at -2 and +2. Now the first thing you want to do is think, alright, go back to the original inequality. We want to know when 64 minus 16k squared is greater than 0. Is greater than 0, positive. So really we're looking to say which of these regions, out of the 3 regions that are set up here, produce an answer when plugged into the original that is greater than 0. So we'll start by looking at the easiest one, which will test 0. So if we test 0 in the original equation, we're going to get 64 minus 0, which is positive. So the middle region on this number line is positive. If we test to the right of the number 2, let's choose the number 3, which is the easiest. If we plug a 3 in for k, we're going to get 64 minus the quantity 16 times 9. And clearly, if you just without even actually getting the value, because it doesn't matter what the value is, all that matters is whether it's positive or negative. And we're going to see here that the quantity 16 times 9 is definitely greater than 64. So 64 minus some number greater than it must be negative. So that region is negative. And now we have to test to the left of -2, so we'll test -3. But what you'll notice is when you test -3, since it's a quadratic in this problem and there's no linear term, we have a function that it'll give us the same answer. So testing -3 now, you're still going to get 64 minus the quantity 16 times 9, which is definitely negative again. Okay? So we have the negative on the outside regions. So we wanted to know when the discriminant will be greater than 0. Well, the discriminant is greater than 0 in this middle region here, and I'll highlight it. From -2 to 2, exclusive. Exclusive, remembering to use our parentheses and not our bracket notation. If we look at it in set notation, we'll use less than symbols instead of less than or equal to, because it's an and statement. So let's write this as a solution set. As a solution set, we have k colon -2 less than k less than +2, which tells us that the answer for k, or the value of k, that will give us a real different set of roots will be any value of k between -2 and 2, assuming that you're not including the endpoints -2 and 2, because clearly the answer for part A was -2 and 2, and those cause the discriminant to be 0. Okay, so it's everything between -2 and 2, but not including the endpoints. And what I want you to do is make sure that you test it. So pick a number for k between -2 and 2, such as 1, or -1, or 0, plug it into the original equation, and determine, and don't try 0, because then it's not quadratic, so it's not going to help too much there. I'd rather you try 1 or -1. And you'll see that when you get those roots, there'll be 2 different real roots. Now, for part C, the question asks us, determine the value of k so that we have imaginary roots. And the only difference now is that we want the discriminant for imaginary roots to be negative. So for part C, we don't have to really redo anything, and you'll see why. So let's scroll this up and show. So for part C, we want to know when the discriminant is less than 0. Well, if we go back to part B, and we look at our number line, when the discriminant is less than 0, it's those regions when it was negative, or less than 0. So all we're looking at now, and I'll highlight it again here, is this region here and this region over here. So when the discriminant is negative, it's everything less than -2 or everything greater than +2. So our solution set will say k colon k less than -2, or, remember it's an or statement, not an and statement this time, k greater than +2. And again, go ahead for this one and test it. Take a value like 3 for k. Plug it back into the original equation we started with, kx squared plus 8x plus 4k equals 0. So take the 3, plug it in for k, and determine the roots you get. And the roots you should get for this will be the imaginary roots. Alright, let's find it. 5. For example 5, you're asked to determine the type of zeros that the following functions will have. And then practice and get a verification or verify this using the calculator program that we wrote. So for the first one, we have f of x equals 2x squared plus 5x minus 4. So for part A, let's start by finding the discriminant. b squared minus 4 times a times c. Okay, so what we get is 25. A double negative is a positive. 4 by 2 is 8. 8 by 4 is 32. 25 and 32. It's going to give us a value here of 59, or 57 rather. Now, if the discriminant is 57, we know that when the discriminant is positive, we have two real different roots. Okay, two real different roots. We can say distinct or different. And remember, if the discriminant had been a perfect square and the b value was rational, then these roots will also end up being rational. But what you'll notice here is that these roots are not rational, they are irrational, because the 57 under the square root cannot be simplified into a rational expression or a rational number. What you end up getting in decimal form for the zeros, if you run it through your calculator program, will be 0.637 and negative 3.137. And this is verified by looking. Our answer was two real distinct roots. They are both real, there are two of them, and they are different or distinct. So part A is verified. Let's take a look at part B now. Part B is 4h squared. Let's write this better. Is 4h squared minus 3h plus 5. And what you'll notice here is our discriminant for this problem is going to be b squared, which is negative 3 quantity squared. Make sure you put that in parentheses. Minus 4 times a, which is 4, times c, which is 5. So what we're going to end up getting here is negative 71. And right away, think to yourself, remember, okay, when the discriminant is negative, it means that there's going to end up being a negative under the radical. And when there's a negative under the radical, we know that the negative under the radical indicates that we're going to have imaginary roots. So these roots are going to be imaginary. There are going to be two of them, and they're going to be complex conjugates. And if you check to verify this on your calculator, the roots you're going to end up getting are going to be 0.375 plus or minus 1.05i. Okay, and again, you can express this in radical form, where you'll have radical 71 in the expression if you use the quadratic formula, but when you check on your quadratic program, it's going to give you the decimal representation. Let's move on to part C now. Part C is the function d of s equals 2s squared minus 16s plus 32. So we have 2s squared minus 16s plus 32. It might be useful for this part to simplify by factoring out a 2. Okay, so we set it equal to 0 to find the zeros of the function. And if we factor out a 2, we get 0 equals s squared minus 8s plus 16. Now where'd the 2 go, you might say? Well, the 2, when factored out, can be divided on both sides, and 0 divided by 2 is still going to be 0. So for a problem like this, we can do it either way. We can go right into finding the discriminant, or we can factor out a GCF, some constant, and divide through by that constant to make it easier on ourselves when determining the discriminant. I don't want to have to square 16 always, so it makes it easier to have the 8 there and the 16 on the end for the c value. So let's take a look at our discriminant now. Our discriminant for this problem is going to be b squared, so negative 8 squared, minus 4 times a times c. Well, the discriminant for this is just going to be 0. You're going to get 64 minus 64, which is just 0. And remember, when the discriminant is 0, the part of the quadratic equation that is under the radical b squared minus 4ac just drops off. So you end up with, for the quadratic formula, remember, negative b plus or minus 0 over 2a. So anything plus or minus 0 is itself, because 0 is the identity of addition. So the identity element of addition tells us that we're going to end up with a solution of just negative b over 2a. So the roots, even though it seems like there would be 2 at first, plus or minus, there ends up just being one root. So it's one real repeated root, which is rational. And if you run this through your equation, so let's write that down first. Real, it's one of them. It's real, it's repeated. It happens to be a double root because it's repeated twice. And it is also rational. And it is rational, and we know that specifically here, and we can check that because b is an integer value, and so is a. So in this point in time, we could say that if we run it through our program, we end up getting values for the zeros of the function that are 4 and positive 4. So both positive 4s, and we can see that it's one root, and it is repeated. And we'll talk more about this in section 7.5 and 7.6 about what this looks like on a graph when it's repeated. Finally, the last example, part D. If we take a look at part D, we're going to see that we have an equation that says 2x squared minus 2x minus 12. Well, clearly, again, start by factoring out a 2 to make it easier on yourself. So this equation results in x squared minus x minus 6. And what we're going to get for this problem is we're going to see that, yeah, we're going to have a discriminant. And the discriminant is going to be negative 1 squared minus 4 times a times c. So it's going to be 1 plus 24, which is simply 25. So this discriminant happens to be positive, so right away we can say that they're real and there are two of them, and they are distinct. But for this problem, because the discriminant is a perfect square, and because the b value is rational, we can also say that the zeros here are going to be rational. Because when you look at the quadratic formula, the quantity radical b squared minus 4ac will simplify to be an integer value. And if you have an integer value plus or minus another integer value all over an integer value, the answer must be rational. So the roots of this one, or the zeros, happen to be negative 2 and positive 3, which verify the answer, or the statement that we've just made, that there are two real, rational, or distinct, two real, rational, and distinct roots. Again, two real, rational, distinct roots. Okay, so again, the checking with the calculator is just to verify that our description of the roots based on the discriminant's value is correct. Okay, that our description is correct. Make sure you take a look at the homework tonight. Numbers 1 through 11 odd, 14 through 26 even, and then 31, 33, 35, and 39. It's a bit of a longer homework. Make sure you take your time and practice and go through each one.